0, I'll have x equals 0, which is exactly the y-axis. So that really is included. How about the x-axis? Well, the x-axis is not included. However, most people include it anyway. This is very common to be a sort of sloppy and bending the edges of corners a little bit, you know, and hoping nobody will notice. We'll say that corresponds to c equals infinity. I hope nobody wants to fight about that. If you do, go fight with somebody else. So if c is infinity, that means the line, little line segment should have infinite slope, and by common consent, that means it should be vertical. And so we can even count this as sort of an isocline, and if, you know, I'll make the dashes smaller to indicate it has a lower status than the others. And I'll put this in, do this weaselly thing of putting it in quotation marks to indicate that I'm not responsible for it. Okay, now, we now have to put in the integral curves. Well, nothing could be easier. I'm looking for curves which are everywhere perpendicular to these rays. Well, you know from geometry that those are circles. So the integral curves are circles. And it's an elementary exercise, and of which I would not deprive you of the pleasure. Solve the ODE by separation of variables. In other words, we've gotten the, so the circles are ones with a center at the origin, of course, equals some constant. I'll call it C1, so it's not confused with this C. They look like that, and now you should solve this by separating variables and just confirm that the solutions are, in fact, those circles. One interesting thing, and confirm this. I won't do it because I want to do geometric and numerical things today. So if you solve it by separating variables, one interesting thing to note is that if I write the solution as y equals y1 of x, well, it'll look like something like the square root of C1 minus, let's make this squared because that's the way people usually put the radius, minus x squared. And so a solution, a typical solution looks like this. Well, what's the solution over here? Well, that one solution only goes from here to here. If you like, it has a negative side to it. So I'll make, let's say, plus. There's another solution which has a negative value. But let's use the one with a positive value of the square root. My point is this, that solution, the domain of that solution, really only goes from here to here. It's not the whole x-axis. It's just a limited piece of the x-axis where that solution is defined. There's no way of extending it further. And there's no way of predicting by looking at the differential equation that a typical solution was going to have a limited domain like that. In other words, you can find a solution, but how far out is it going to go? Sometimes it's impossible to tell except by either finding it explicitly or by asking a computer to draw a picture of it and seeing if that gives you some insight. It's one of the many difficulties in handling differential equations. You don't know what the domain of a solution is going to be until you've actually calculated it. Now, a slightly more complicated example is going to be, let's see, y prime equals 1 plus x minus y. It's not a lot more complicated. And as a computer exercise, you'll work with still more complicated ones. But here, the isoclines would be what? Well, I set that equal to c. Can you do the algebra in your head? An isocline will have the equation, this equals c, so I'm going to put the y on the right-hand side and that c on the left-hand side. So it will have the equation y equals 1 plus x minus c. Or a nicer way to write it would be x plus 1 minus c. I guess it really doesn't matter. So there's the equation of the isocline. Let's quickly draw the direction field and see what... notice, by the way, if it's a simple equation, but you cannot separate variables. So I will not, today at any rate, be able to check the answer. I will not be able to get an analytic answer. All we'll be able to do now is get a geometric answer. But notice how quickly, relatively quickly, one can get it. Some feeling for how the solutions behave to this equation. All right. Let's see. What should we plot first? I like c equals 1. No, don't do c equals 1. Let's do c equals 0 first. C equals 0, that's the line. Y equals x plus 1. Okay, let me run and get that chalk. So all isoclines are in orange. If so, when c equals 0, y equals x plus 1, so let's say it's this curve. C equals 0. How about c equals negative 1? Then it's y equals x plus 2. It's this curve. Now let's label it. Let's label it down here. So this is c equals negative 1. C equals negative 2 would be y equals x. No, what am I doing? C equals negative 1 is y equals x plus 2. That's right. Well, how about the other side? If c equals plus 1, well, then it's going to go through the origin. Looks like a little more room down here. How about that one must, so if this is going to be c equals 1, then I sort of get the idea. C equals 2 will look like this. They're all going to be parallel lines because all that's changing is the y-intercept as I do this thing. So here it's c equals 2. C equals, that's probably enough. All right, let's put in the line elements. All right, c equals negative 1. These will be perpendicular. C equals 0, like this. C equals 1. Oh, this is interesting. I can't even draw in the line elements because they seem to coincide with the curve itself, with the line itself. They lie along the line, and that makes it hard to draw them in. How about c equals 2? Well, here the line elements will be slanty. They'll have slope 2. So it's pretty slanty up. And I can see for c equals 3 in the same way. They're going to be even more slantier up. And here they're going to be even more slanty down. This is not very scientific terminology or mathematical, but you get the idea. Okay, so there's our quick version of the direction field. All we have to do is put in some integral curves now. Well, looks like it's doing this. It gets less slanty. Here it levels out, has slope 0. And now in this part of the plane, the slope seems to be rising, so it must do something like that. This guy must do something like this. I'm a little doubtful of what I should be doing here. How about going from the other side? Well, it rises, gets a little... Should it cross this? What should I do? Well, there's one integral curve which is easy to see. It's this one. This line is both an isocline and an integral curve. It's everything, except drawable. So, okay, you understand this is the same line. It's both orange and pink at the same time, but I don't know what combination color that would make. It doesn't look like a line, but you know, be sympathetic. Now the question is, what's happening in this corridor? In the corridor, that's not a mathematical word either, between the isoclines for, well, what are they? They're the isocline for c equals 2 and c equals 0. How does that corridor look? Well, it's something like this. over here, the lines are all look like that, and here they all look like this. The slope is 1, slope is 2. And a hapless solution gets in there. What's it to do? Well, do you see that if a solution gets in that corridor, an integral curve gets in that corridor, no escape is possible. It's like a lobster trap. You know, the lobster can walk in, but it cannot walk out because the things are always going in. How could it escape? Well, it would have to double back somehow, and remember, to escape, it has to be, to escape on the left side, it must be going horizontally. But how could it do that without doubling back first and having the wrong slope? The slope of everything in this corridor is positive, and to double back and escape, it would at some point have to have negative slope. It can't do that. Well, could it escape on the right-hand side? No, because at the moment when it wants to cross, it will have to have a slope less than this line, but all these spiky guys are pointing, it can't escape that way either. So no escape is possible. It has to continue on there. But more than that is true. So solution can't escape. Once it's in there, it can't escape. It's like those, what do they call those plants? I forget. Pitcher plants. You know, all the hairs are going down, so it looks like that. And so when the poor little insect falls in, it could climb up the walls, except that all the hairs are going the wrong direction and it can't get over them. Well, think of it that way. This poor trapped solution. Well, so it does what it has to do. Now, there's more to it than that, and because there are two principles involved here that you should know that help a lot in drawing these pictures. Principle number one is that two integral curves cannot cross at an angle. Two integral curves can't cross I mean by crossing at an angle like that. I'll indicate what I mean by a picture like that. Now, why not? This is an important principle. Let's put that up in, at least in a white box. They can't cross because if two integral curves are trying to cross, well, one will look like this because it's an integral curve because it has this slope, and the other integral curve has this slope, and now they fight with each other. What is the true slope at that point? Well, the direction field only allows you to have one slope. If there's a line element at that point, it has a definite slope, and therefore it cannot have both this slope and that one. It's as simple as that. So you can't, the reason is you can't have two slopes. The direction field doesn't allow it. Well, that's a big, big help, because if I know here's an integral curve, and if I know that none of these other pink integral curves are allowed to cross it, how else can I do? Well, they can't escape, they can't cross. It's sort of clear that they must get closer and closer to it. You know, I'd have to work a little to justify that, but I think nobody would have any doubt of it who did a little experimentation. In other words, all these curves join that little tube and get closer and closer to this line y equals x. And therefore, without solving the differential equation, it's clear that all of these solutions, how do they behave? As x goes to infinity, they become asymptotic to, they become closer and closer to the solution x. Is x a solution? Yeah, because it's an integral. Y equals x is an integral curve. Is x a solution? Yeah, because if I plug in y equals x, I get what? On the right-hand side, I get 1, and on the left-hand side, I get 1. 1 equals 1. So this is a solution. Let's indicate that it's a solution. So analytically, we've discovered an analytic solution to the differential equation, namely y equals x, just by this geometric process. Now, there's one more principle like that, which is less obvious, but you do have to know it. And so they're not allowed to cross, that's clear. But it's much, 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 much less obvious that two integral curves cannot touch. That is, they cannot even be tangent. Two integral curves cannot be tangent. I'll indicate that by the word touch, which is what a lot of people say. In other words, if this is illegal, so is this. Can't have it. You know, without that, for example, I might feel that there would be nothing in this to prevent those curves from joining. Why couldn't these pink curves join the line y equals x? You know, it's a solution. They just hitch a ride, as it were. The answer is they cannot do that because they have to just get asymptotic to it, ever closer. They can't join y equals x because at the point where they join, you'd have that situation. Now, why can't you have this? That's much more sophisticated than this, and the reason is because of something called the existence and uniqueness theorem. Existence and uniqueness theorem, which says that there's, through a point x0, y0, that y prime equals f of xy has only one and only one solution. One has one solution. In mathematics speak, that means at least one solution. It doesn't mean it has just one solution, okay? That's mathematical convention. It has one solution, at least one solution, but the killer is only one solution. That's what you have to say in mathematics if you want just one. One and only one solution through the point x0, y0. So the fact that it has one, that's the existence part. The fact that it has only one is the uniqueness part of the theorem. Now, like all good mathematical theorems, this one does have hypotheses. So this is not going to be a course, I warn you, those of you who are theoretically inclined, very rich in hypotheses, but you do have to, the hypotheses for this one are that f of xy should be a continuous function. Now, you know, like polynomial signs, stuff like good, should be continuous near, in the vicinity of that point. That guarantees existence, and what guarantees uniqueness is the hypothesis that you would not guess by yourself. Neither would I. What guarantees the uniqueness is that also its partial derivative with respect to y should be continuous. Should be continuous near x0, y0. Well, I have to make a decision. I don't have time to talk about Euler's method. Let me refer you to there's one page of notes, and I couldn't do any more than just repeat what's on those notes. So I'll trust you to read that, and instead let me give you an example which will solidify these things in your mind a little bit. I think that's a better course. The example is not in the notes, and therefore, remember, you heard it here first. Okay, so what's the example? It's So, here's our differential equation. Now let's just solve it by separating variables. dy, can you do it in your head? dy over dx, put all the y's on the left, it will look like dy over 1 minus y. Put all the dx's on the left, so the dx here goes on the right rather. That will be dx, and then the x goes down into the denominator, so now it looks like that. And if I integrate both sides, I get the log of 1 minus y, I guess maybe with a, oh, I never bother with that, but you can. It should be absolute values, but all right, put an absolute value. Plus a constant, and now if I exponentiate both sides, the constant is positive, and so this is going to look like 1 minus y equals x. And the x constant will be e to the c1, and I'll just make that a new constant, cx. And now you can fuss, by letting c be negative, that's why you can get rid of the absolute values, if you allow c to have negative values as well as positive values. Let's write this in a more human form. So that's y is equal to 1 minus cx. Good. All right, let's just plot those. So these are the solutions. Pretty easy equation, pretty easy solution method, just separation of variables. What do they look like? Well, these are all lines whose intercept is at 1, and they have any slope whatsoever. So these are the lines that look like that. Okay, now let me ask, existence and uniqueness. Existence. Through which points of the plane does a solution go? Answer, through every point of the plane, through any point here, I can find one and only one of those lines, except for these stupid guys here on the stalk of the flower. Here, there is no, for each of these points, there is no existence. There is no solution to this differential equation which goes through any of these wiggly points on the y-axis. With one exception, this point is oversupplied. At this point, it's not existence that fails, it's uniqueness that fails. No uniqueness. There are lots of things which go through here. Now, is that a violation of the existence and uniqueness theorem? It cannot be a violation because a theorem has no exceptions, otherwise it wouldn't be a theorem. So let's take a look. What's wrong? We thought we solved it, modulo putting the absolute value signs on the log. What's wrong? The answer, what's wrong is, to use the theorem, you must write the differential equation in standard form, in that green form I gave you. Let's write the differential equation the way we were supposed to. It says dy dx equals 1 minus y divided by x. And now I see the right-hand side is not continuous, in fact, not even defined when x equals 0, when along the y-axis. And therefore, the existence and uniqueness is not guaranteed along the line x equals 0, the y-axis, and in fact, we see that it failed. Now, as a practical matter, it's the way existence and uniqueness fails in all ordinary life work with differential equations is not through sophisticated examples that mathematicians can construct, but normally because f of x, y will fail to be defined somewhere, and those will be the bad points. Thanks.